Well, it's on a dreary, rainy day in late December that I begin this series of videos on analytical geometry. Analytical geometry is usually a one-semester course in a two-course series in preparation for calculus in high school. So you might take analytical geometry one semester and something called trigonometry, which is the math of triangles, in a second. All of these can be bundled together as a pre-calculus kind of series of course that's often taken in the 11th grade in high school. And so I begin today. I wanted to come up with a Scottish accent, but I couldn't pull it off. It just sounded silly. Maybe it'll creep out in this rainy, very cold and wet, damp day in December in Indiana. But that's not important. We're here for analytical geometry. What is analytical geometry? Analytic geometry is the study of geometry using a coordinate system. A coordinate system? What's a coordinate system? Well, the coordinate system is the x, y. No, I'm not a vampire, or you're not a vampire, rather. I would be the one protecting myself from you. Maybe we're protecting ourselves from analytic geometry. But a coordinate system is an x, y. Well, it doesn't have to be x, y. You could be something in time. Could be anything. Could be A, B. Could be sales and profit. Doesn't matter what the coordinate system labels are, but analytic geometry is geometry that is plotted on a on a coordinate system, which was an ingenious idea that René Descartes, yes, he's French, so he doesn't pronounce his name right, but René Descartes in the late 1500s and early 1600s, I believe, came up with analytic geometry. He was a brilliant guy. I hate him, even though he's dead. But basically, he developed this coordinate system, and for this reason, his name's Descartes. The XY coordinate system that you have come to know and love, probably in an algebra or geometry class already before you would be looking at these videos, that is called the Cartesian coordinate system because it was originated by Descartes. This allowed math to jump incredibly beyond what the Greeks and others had been able to do. This analytic system, this way of plotting and graphing, suddenly made it possible to do things with math that the Greeks were never able to do. It's just incredible breakthrough. These people were so smart, it just drives me crazy. And so you can see in this typical Cartesian coordinate framework, you have the x as the horizontal and the y as the vertical. It wouldn't have to be that way, but that's where we usually start. And so usually the first number, see the 2, 2 there, not a 2, 2, but the 2, 2 there is a point that I have graphed on this Cartesian coordinate framework. The first number is the x or horizontal number, and then the second is the y or the vertical number. It wouldn't have to be that way, but that's the convention. That's the way we do it. So if I put in parentheses a point 2, 2, I'm saying that to locate this point, you go across to the x equals 2 and up to the y equals 2, and that's where you'll find the point. And you can see it. Look at the point. There it is. I've made a point. It's right there. So anyway, this probably is very familiar to you, but just to give you a sense of where we're starting in this analytic geometry series of videos. So this first video is about graphing equations. You know, chances are, if you're watching this video or if you're in an analytic geometry course or a pre-calculus course, you've already graphed your fair share of equations. You should get some kind of a badge saying, I graph equations. The easiest way, well, let me start talking about variables and such. A variable, basically, it's usually a letter that we use as a placeholder for a number. So x doesn't mean just one number. X can mean what we might call a domain of numbers, a set of possible numbers. It could be all real numbers. You know, the domain of x, that is the numbers that could be x, could be all numbers. This is a little abstract. Once it clicks, it's not hard. But basically what I'm saying is that x's and y's aren't specific numbers. They represent a set of possible numbers. In space, if you take of this space in front of me, there are lots of possible spaces in front of me. And so it could be that I am graphing a whole bunch of points in this space here. So by the x's, we're referring to where in this horizontal framework the point is, and by y we're talking about where in this vertical framework the y is. So x and y don't represent a specific point. They represent x represents a domain of possible points, and then y a range of possible other values that go along with the x. Am I just making it more complicated? Hopefully you know all this from prior courses. You probably shouldn't be starting analytic geometry if you don't understand x's and y's a little bit already. So let's take a equation like 2x plus y equals 6. This is an equation in two variables where x and y are the variables. And you can have more equations. You have equations in 3 variables, 4 variables, 5. I mean, really, the sky's the limit as far as until you have to use the restroom, and then you have to stop. But so we're going to start off this series of videos with equations in 2 videos. Later, by the way, we'll learn about functions, just to prime the pump. A function is a special kind of relationship between x's and y's, where there's only one and only one y for every x. It's a special kind of equation in 2 variables that we'll be looking at in this series of videos. And then, of course, if you go on to calculus, you'll do functions extraordinaire. But just if you don't understand functions yet, don't worry, there'll be a video yet to come. Now, let's get back to the simple matter of graphing equations. So there are different ways to solve a problem. You can solve it by graphing, and basically, if you can get the basic sense of a graph of an equation in 2 variables, then you can kind of predict where the graph's going to go. But before you get there, you might start by plotting a kind of table. So let me just show you a table. There's a table where I've put x in one column and y in another, and I've kind of substituted some numbers to see what that's kind of the numerical way of approaching a problem, where you can figure out what it is at a certain y by just plotting in x's until you figure it out. And so those are 2 ways to approach a problem. One is by numerical, just plotting numbers, and the other is by graphing, which is what this video is allegedly about. So you can get a basic sense of a graph by plotting points on it. You put in a value of x and see what y comes out. Then put the point on a graph. So going back to my equation 2x plus y equals 6, if I substitute in an x as 0 into this equation, so 2 times 0 is 0, that goes away, and I'm left with y equals 6. Yay! So that tells me that 0, 6 is a point on the graph of 2x plus y equals 6. So I can just basically plot points like this, or use a table to come up with values of y's for values of x's. So I know that 0, 6 is a point on the graph, and 1, 4 is a point on the graph, and negative 1, 8 is a point on the graph, and 2, 2 is a point on the graph, negative 2, 10 is a point on the graph, and I might plot them like this. Now, of course, it should be a solid line, but for various reasons that I won't tell you right now, but you may already know, this equation, 2x plus y equals 6, is a line. And so it should be solid. I've rather than obliterate the points by drawing a line through them, I've gone ahead and left the points there. But you can see that I can predict kind of where this is going to go by graphing. So I hope this is all old business. If you're watching this video at the beginning of an analytic geometry or pre-calculus course, I hope that you have some sense of this already. Okay, now, what might be helpful review is some graphing shortcuts, because not all graphs are going to be as simple as the one I just plotted. So, intercepts. Intercepts are basically where a graph crosses either the x or the y line, or if you have a z line or another line, you know, whatever. But whenever a graph crosses one of the coordinate lines, that's called an intercept. So there's an x-intercept where it crosses the x axis. Now, it can cross more than one. You can have a line that just goes up and down and up and down. I mean, there could be an infinite number, like this. If it's a sine wave, there would be an infinite number of x-intercepts because it goes up and down and up and down. You know, but most graphs that you'll be dealing with in this course won't be like that. And so an x-intercept is where a graph crosses the x-axis. A y-intercept is where a graph crosses the y-intercept. So if you have a circle graph, it's going to cross. It might not be on the x-axis, but if a circle crosses the x-axis, then it's going to have two y-axis. It's going to have two y-intercepts. So how do you find an intercept? It's very easy, because any place where a graph crosses the x-axis, x is going to be 0. I am sorry. Any place, forgive reversing, any place where a graph crosses the x-intercept, y is equal to 0. And any place where a graph crosses the y-intercept, x is equal to 0. It's the opposite. So if you set y equal to 0, y equal to 0, that's going to tell you the x-intercepts. And if you set x equal to 0, that's going to tell you the y-intercepts. Sorry, I botched up the start of that. But again, it's very simple, because by definition, an x-intercept is where a graph crosses the place where y equals 0. And by definition, a y-intercept is a place where a graph crosses the x equals 0 line. So it's very simple to find the intercepts. You simply set y equals 0 and solve, or set x equals 0 and solve. Symmetry is another thing that can help you graph. So for example, if both x and if both y and negative y are on the graph, then it's symmetrical in relation to the x-axis. Similarly, if both x and negative x are on the graph, then it's symmetrical in relation to the y-axis. And if both x and negative x, as well as y and negative y, are in the graph, then it's symmetrical in relation to the origin in the center. Well, not my best video, but hopefully it gets you launched into analytic geometry or pre-calculus with some basic reminders of things you probably learned in a previous course about graphs and some of the basic features and shortcuts of graphing.